Good morning. Welcome to Chapter 13, Concurrent Programming. Lecture 1, Background and Motivation. In this chapter, I would like to talk about the parallelism and how to implement the parallelism in language level. And what are the parallelisms that we usually see in programming language? We have vector parallelism, and that usually is at two levels. One is operator level, the other one is a loop level. So operation level actually is an operator code, or actually is a instruction level below the instruction level. So basically, you can do a systoglic array to provide different data to go into a systoglic array to help you to achieve some calculation, something like metric calculation. But that is actually below a instruction. And another one is in the loop level, you can use a vector processing, for example, parallel for loop or something like that to achieve that. That's another vector parallelism. And we also have instruction level parallelism. We have already discussed this many times. It includes the pipelining, super pipelining, superscalar, VLIW, out of order execution, and many things like that. And loop level parallelism, including the loop unrolling and the parallelism using the for loop, parallel for loop. And then task level parallelism, we have multi-threading and multi-processing. And these are two concepts, but sometimes they are mixed. And then we have program level parallelism. We have distributed computing and message passing computing. So here we have 5 different levels of parallelism for us to discuss. And in this chapter, we mainly focus on the programming language feature. So it will be basically just focus on these two mainly. And then instruction level may be lightly, vector level may be lightly, and this one very light. Topics in concurrent programming, including the hardware and memory model that is related to computer architecture. And then second, we have the thread process program management that is related to OS and language. Third one is data synchronization that is related to memory model and programming language. Performance optimization, that's utilization of parallelism, and that is related to your hardware or software design. And then race deadlock issues, these are the problems that we try to avoid in the concurrent programming environment. So we have single threading, then multi-threading, then multi-processing, and then multi-programming. Here we would talk about these 4 different terms. And single threading is a single thread. That's traditional computing, that you only have one thread to execute. Then there is a programming image for each thread. And in fact, in the old days, it's called single processing, not single threading, because at that time, there is no concept of thread. And later, when multi-thread become available, we have the single event loop to handle the multiple thread. And then later, start to have parallel environment with event-driven programming to handle multi-threading. And then later, we have multiprocessor to handle the multi-threading. And later, the thread and process are expanded to programs, so multiple programs can be run in the same machine or in the same multi-core environment. Background and motivation. Process or thread is a potential active execution content. And in fact, in the old day, we talk about it as the program image. And the program image is a process. So a process has a process image, and you have a program in the disk. And that got loaded to the memory is called process image. And inside process image, you have your code segment, data segment, your actual segment, those kind of information. And actually, this is more like a C language type of the data frame, and you have the process data also related stores in the process image. And that's the old day, that's the classic Newman machine model. And later, this process image can be expanded and can actually was added with more information to accommodate the multi-threading environment. And parallel programs have more than one of the process running at the same time. A process can be thought of a abstraction of physical processor. That's from user or programmer point of view. It can be viewed as a physical processor, but in fact, it may be not. It may be just a time-shared environment, and you actually sharing a single CPU, but multiple threading being implemented in that single processor. But nowadays, because we have the multi-core CPU in our even in the microprocessor, so in fact, this is not no longer an issue. Nowadays, there is very few personal computers still ship with single processor. It's all multi-core now. Background and motivation, multi-threading, multi-programming, and distributed programming. Multi-threading in fact means I have a machine, I run multiple program image, we call it thread, inside this CPU. And then it actually share and scheduled by some processors scheduling. And this may be shared by one program. But multi-programming means in your CPU, you actually allow multiple programs. Each one of them may be something like this to run at the same time, and then they may pass message or use socket to talk to each other, or even for the remote side. And that for remote side is called distributed computing. So process thread can come from multiple CPU, kernel level multiprocessing of a physical machine, and then language or library level or multiprocessing of kernel level abstraction. They can run in true parallel or unpredictably interleaved or run until blocked. Most work on first two cases. They are equally difficult to deal with. True parallel means you need to have multiple processor that can, or multiple core that can allow you to do it in parallel, that has hardware overhead. And unpredictably interleaved means that you have actually use time share scheme to support a multi-threading or multiprocessing. Run until block means you actually own the CPU until you got kicked out because of the operation system's priority queue to actually kick you out after you have spent enough time in there, to be fair among the different processes. Background and motivation, two main classes of programming notations. First one is synchronized access to shared memory. Second one is message passing between processes that don't share memory. Both approaches can be implemented on hardware design for each other, and then low shared memory on message passing hardware tend to be slow. Let me explain this. What it actually is. Because we want to do parallel programming, so one thing we can do is a synchronized access to shared memory. So we actually have a system bus, and then there's a main memory, and then there are several cores, or maybe one core, and each one of them may have a cache, and all of them connected to a bus. And then I have a process 1 running on here, I have a process 2 running on here, and we have process 3 running on here, all sharing a certain memory, and they may have to have coherent control in order to make them successful. And this actually can also do message passing if you want to actually pass the information to different process. So, but this one is actually a shared memory model. And there is another one called message passing that actually you don't care about a shared memory. You actually have one process. Conceptually, you just have one process. The other one, I send you by message, I receive it, just like HTML request. And you provide the result for the HTML request. Those kind of handshaking type of information exchanging is called message passing. So the shared memory on message passing hardware tend to be slow because it's not actually down to the lower level to process it. Level of abstractions. We have instruction level, method level, task level, program level, and system level. So on the left-hand side, we have breadbox parallel library. So in this one, actually, the level of the abstraction actually depend on the programming environment or the library. So we have C# library, we have the breadbox parallel liquid library, and the C# virtual basic. Those kind of different language can access the same library in parallel format, and that actually will provide you some sort of the parallel FX for the task and program level, method level support. And TPL is another task level processing, so that actually made this parallel for loop possible, and that is a loop level. That is actually a vector processing by performing at root level. So we need to know about what parallelism we are dealing with and what are available in our programming environment. Background and motivation. Now we are looking at what be the problem in our parallel processing environment. The first one is race condition. And then because of this problem, when we design our parallel processing environment, we need to take care of these problems. And then they have special demand on the programming language, and that is what we want to learn as a programming language developer about what actually need to be deal in the language level, and to support computing or parallel processing in instruction level or in task level or in method level. So now let's look at what is race condition. A race condition occurs when actions in two processes are not synchronized. So here, actually, I have a full function, and I have a zero count, and then I accept a parameter n, and then my return value is like this, And then here, my return value, if 0, then I increase my zero count. So zero count is a global variable. And for this, actually, this zero count is shared by multi-thread with many different functions all around this full function. And at the instruction level, actually a compiler to this zero count assigned to R1 and R1 increase, and then we update the zero count. So here is a function, is an assembly call for the zero count increase. Now, what is the problem? The problem is these two may actually in competing situation. For example, I get a zero count, and that zero count at the moment is 1. So I do this, and then I want to assign to my zero count that will become actually this one I should become what? Should become 2. And here actually right here it increased by 1. So right here we have this zero count, and when this zero count actually updated, and then this one may update the R1 to increase by 1 as well. So at this time it may actually affect this R1 over here. So you may actually increase by 2 instead of increase by 1. So that actually is actually a problem. And maybe the R1 got updated by the other one. When you fetch, that is actually original one, and then that R1 being set by the same different process by 1, and you will see different copy. So if the instruction interleave roughly as shown, both threads may load the same zero count value, but in fact, actually, this thread 2 should be after this thread 1 that would have the safe data. So both may increase by 1, but both store the greater value, that is only 1 back to the 0 value. And then actually at the end, thread 2 is not getting the right zero count at the beginning, and then may end up saving the same value to zero count, and then zero count only increased by 1. So that is some problem that can occur. And maybe in the middle, you miss up somewhere. The R1 data may also be messed up. So background and the motivation. Race condition that we actually write this. So actually what happened is, if the instruction actually is not overlapping, has mutual inclusive access, then the data here will be passed to here, so it will be fine. But if the two is in race condition, same time or one before the other one, and then maybe some of the data will not be consistent. So we need to have some language level mechanism to avoid that. So race condition, we want to avoid race conditions. Suppose processor A and B share memory and both try to increment variable X at more or less the same time. Very few processors support arithmetic operation on memory. So each processor execute load X to some register, and then increase and then store register X content to the memory. And suppose X is initialized to 0. If both processors execute these instructions simultaneously, and what are the possible outcomes? Could go up by 1 or by 2. So actually that depends on whether that has the race condition or not. Synchronization. Synchronization is the act of ensuring the event in different process may happen in desired order. Synchronization can be used to eliminate race conditions. So we talk about this parallel processing environment, And number one thing we talk about is the race condition. Now we provide an answer to submit. It's called synchronization. So synchronization of the programs can eliminate the race condition. In our example, we need to synchronize the increment operations to enforce mutual exclusion. And we will talk about this idea of mutual exclusion later. Excuse me. Most synchronization can be regarded as either mutual exclusion or condition synchronization. So the synchronization scheme may have the mutual exclusion on a critical region. So you run your program and somewhere there is a critical region, and the other program also write its own, and there is a critical section. So we actually will allow only one guy to go through it. It's just like two cars go to a narrow bridge and not only allow one car to pass. So this is critical section. So we will just allow one car to go through, and then car from the other side, after he or leave, you come in and get across the bridge. That's actually mutual exclusive access. Condition synchronization, which means making sure that a given process does not proceed until some condition holds. So this actually is need to check the conditions. So now let's look at what is a critical section. A critical section is actually has all we call the critical region is atomic code block. So that code block, you can only allow one process to get in. So one way to do this is use lock unlock. So when you go into a critical section, for example, you want to change the bank account money, and then there are several people may also update the data at the same time, including the bank itself, the customer itself, and then maybe multiple customers like your wife, your children, who want to access your bank account. Then you need to set up a lock unlock or a critical section, so only one person can get into there at once. And there are some other schemes that can perform similarly for this critical section is the wait and signal mechanism. And that is similar. And this one is to acquire lock, and I can go in. And then when I finish, I unlock it to allow other people to go. But if you do a lot of job here, you actually won't be kicked out. So you may actually end up taking a lot of time, or even sometimes the deadlock may happen. And here we have wait signal. So wait signal is like when we will enter into a critical section, it will wait until the other guy signal it to get in. So wait signal is different from lock unlock. Actually, when you go through to this here, you will actually wait there until there is another one allow you to get in the run, and you finish its own call section. And then you get in, and then when you finish, you enforce some other people to get in as well. So that actually is a way signal scheme. Third one is sophomore. Sophomore is actually similar to wait and signal. So you have similar program structure. Background and motivation. One might be tempted to think of mutual exclusion as a form of condition synchronization. Actually, these two terms are different. Mutual exclusion and condition synchronization, they are two different terms. One may implement the other, but they actually are not the same. The condition being that anybody else in the critical section, but not, it is not. Actually, these two are different terms. So the distinction between basic between is existential or universal qualification. Mutual inclusion require multi-process consensus, and we do not, in general, want over synchronize. To eliminate parallelism, which we generally want to encourage the performance. And basically, we want to eliminate bad race condition. For example, the one that caused the program to give incorrect results. Background and motivation. To implement synchronization, you have two steps. Something that's atomic. Atomic means is a single unbothered code segment. It actually can be independent from other code segment. It can run by itself. And that can be shared by different processes. We call it atomic functions. It means it happens all at once as indivisible action. And in most machines, read and write of individual memory locations are atomic. So basically, those shared memory model can be implemented by shared operation, such as the one we have here. And in early machine, read and write of individual memory location were all that was atomic. So we try to have atomic access to the individual memory. But the problem again, atomic will slow down the whole processor efficiency. So people think about a lot of workaround to solve the problem. To simplify the implementation of mutual inclusion, hardware designers begin in the late 60s to build so-called read, modify, write, fetch, and find instruction in two-layer machines. So we'll talk about this. Now, let's look at different concurrent programming mechanisms. Chapter 13, Lecture 2, Multi-threaded Programs. The first mechanism we will talk about is the coroutines. Coroutines are computer programs components that generalize subroutine for non-preemptive multitasking. By allowing multiple entry points for suspending and resuming execution at certain locations, coroutines are well suited for implementing more than familiar program components such as cooperative task, exception, event loop, iterator, infinite list, and pipes. So coroutine is a basic mechanism. Basically, you have the execution flow like this. You go to the other program and run, and then come back. Something like this. These coroutine, these two subroutines are called coroutine. And then it is the basic mechanism to support the cooperative tasks, exception, event-driven programming event loops, iterators, infinite list, and pipes. Pipes are for communication. IPC, inter-process communication. So coroutine is a key concept that first invented for the concurrent programming. But later, there are several different mechanisms following the footsteps of the coroutine. But now let's look at the coroutine. So producer-consumer model, say we have a producer, it actually will loop while queue is not full, then you actually create some new items. So basically you have a queue and then it is not full, so you keep producing something. And then the consumer is taking out scene from here. So as long as the queue is not empty, the C can actually continue to take out something, and the P can continue to provide something there. And then if actually Q is full, then this producer will stop. Wait until the consumer to take out something, then you will wake up P to do it. As the producer consumer model, and it actually is usually work for some buffer like this, or some queue. And that's one model usually used for the concurrent programming. So it's a discrete event simulation for concurrency. But it actually can be for single-threaded environment to simulate the concurrency. And here we have the coroutine model. We have coroutine A, B, and C. And it gets started like this, and then call coroutine 2, and then go to coroutine 3, C, and then doing like this. So it's rotating it among 3 coroutines as the execution flow. So that's coroutine, and coroutine is used to implement some model like producer, consumer. And right here we have maybe have a main program, jump to connection 1, and this can be of different process or even different machine. So you have a main loop, and then there's a connection waiting for internet response or something. So this can be something like HTML request, and then wait for something to return some result. So it achieves time shared concurrency in centralized or distributed environment using the coroutine. Coroutine for asynchronous control flow. So coroutine say control flow actually is asynchronous. So you don't know when it will be returned. So it's not cycle based. So it's not actually being synchronized in clock cycles or any time based. So it's actually asynchronous. And then it's good for web application, event loop, reception, cooperative task as a producer consumers. And you actually can have multiple coroutine in Python environment. And they are threads, several threads, and each one may have many coroutines. So Python is a good example for using the coroutines. Web browser parsers. Here we give you an example of web browser parsers. A web browser itself can be a compiler because usually you need to process the HTML and JavaScript programs. So it's thread-based code actually from a hypothesis web browser. So this one doesn't is not a real web browser, but it actually is a model. To first approximation, the parser page subroutine is the root or recursive descent parser of HTML. So web browser itself can be a parser, and here we talk about a recursive descent parser for HTML. In several cases, however, the action associated with the recognition of construct background image table or frame set. These things actually will take more time. Say I have a web page. And then here's an image, here's a video, here can be a table, and those image or video can need longer download time. Say let's try this. Let's go to a web browser. And let's try, say, let's try here. And then let's try Yahoo. But some of the image frame, or this one is actually quite quick. But some of the web page, if the bandwidth is not shown quick enough, then it will actually take longer time. Nowadays, actually, the button actually is a little bit slower, as you can see. But okay, that's about this web browser thing. So we don't want the main program got hold up by this download of some components. So we want the download to be proceeding in concurrent format. So we actually want the download to be in concurrent format, continue passing the page itself. In this example, concurrent threads are created with a fork operation. An additional thread would likely execute in response to keyboard or mouse events. So right here, let's read the program. We have a procedure pass page. So we have the parser HTML header, and usually you have something like in your HTML program, you have like a slash, you have the HTML something, and then at the end you have HTML, and here you have header, and you may have end of header, right? You have body, and like end of body, something like this. So the header part, it will be passed first in this program, and then you will check the current token, see what token it is. So if some token is easy, like PHUL, unlisted, unordered list, or header one or paragraph, it can be just be passed quickly. And if it's background, then we will fork a render background to get an image. So for image, we will render a fork render image. Table, we will fork a form tables. Friend set, we will actually pass the friend list and then match this to do that. And then here, the pass friend, you will actually fork a friend for format friend pass. So actually, all of these heavier items will be forked as different process. So actually, you have the main flow starting the passing for header, and then once you meet a image, once you see an image, you may actually fork. So for fork actually is divide your execution flow to two. And then later, once they finish, they'll join together. So there should be a fork and join pair in your thread management. Say if there is no such thing, then you actually will have to wait until some image be download until it actually sees something. So this actually is good to reduce the latency or the user's inspection time. So dispatch loop alternative. Dispatch loop browser data structure with dispatch loop keep track of all the tasks the browser had yet to complete. So dispatch loop browser is a keep track of all the tasks. So it's like a dispatch panel. So everything come to this point and it check what we need to dispatch to fork out and then wait for it to come back. So that's called dispatch loop. And then it must identify these various tasks or image of the page image table frame set so that we can find them all and then claim their state if the user click a stop. So you do something and then you try actually download some image, but in the middle you may change it for different pages. So that download will be stopped. So that actually is a dispatch control loop. And to guarantee good iterative response, we must make sure no sub-action continue task take very long to execute. The principal problem of a dispatch loop beyond the complexity of subdividing tasks and saving state is that it hides the algorithmic structure of the program. For distinct tasks could be described elegantly with standard control flow mechanism. So each program can be described in the standard if then else and then loops. If not for the fact that we must return to the top of the dispatch loop every delay induced the operation. So each time we need to go back to the top of the dispatch loop. In effect, the dispatch loop turns the program inside out, making the management of tasks explicitly and the control flow within tasks implicitly. So we try to manage the control either to kick out some process or terminate some process. Those parts are taken implicitly. But the task running itself is implicitly. You don't actually know. The resulting complexity is similar to what we encounter when we try to emulate a recursive set with iterated object, or worse. Like truly iterators, a thread package turns a program right side out, making the management of task threads implicitly, and the control flow within the thread implicit. So actually, this is the dispatch loop alternative for the browser. Dispatch loop alternative. Let's look at the loop code. So here, what is the dispatch loop? We actually receive different function that we need to run. So this got pipe actually got queue up for different things, like okay, we receive a repen, and we receive a mouse action, and we receive several things. These we actually call them events. So actually they are events put into a queue, and then there's a dispatch loop, we call it event loop. And actually this event loop idea is used for JavaScript. So we serve one by one for that using this dispatch loop. And it's actually a serial execution to mimic the concurrency. So we actually have a loop, okay, and then if a new event is available, and then if existing task is waiting for E to continue E function, then we do it. Otherwise, if E can be handled quickly, so do so, or allocate and initiate a new task to continue E. So basically, this is to use the handler, the event handler for these different events. So this is the loop, and it will go back to here if the ready task is non-empty, and then you will pick one. If there's no one in the execution loop, we will pick that task, and then it should come back to run the loop. So each time this ready list is the queue we talk about, is the dispatch queue. And then if they got serviced, they will actually go to run it and then return to it. This is called dispatch loop browser. and JavaScript is similar to this dispatch loop. Now let's look at the memory coherence in concurrent environment. We have processor A, processor B, processor Z. Okay, the event loop and web browser actually happen in the web application. And web application, we have a web page with a browser, and then you actually do some query, and that query actually kick out some process actually in the remote side and wait for it to return. That actually makes some HTML request or something, and there is a response coming back, and the engine actually has the different event queue, and then there's an event loop to handle it. That's the environment we have, and that is a concurrent programming environment because your local need to wait for the server to finish, and the local may have multiple events going on. That's one thing. Now, this memory coherence model is different. Memory coherent model is actually, for example, it happened for a multi-threading environment. Now we have multiple variables, so some program got allocated to here, some program got allocated to here, some program got allocated to here, and each one is forked out to a processor, but eventually it will actually access the same memory to maintain the program consistent because we have some variable for them. So if that happens, and then you need to maintain the coherence for those different threads, and that is the issue for memory coherence problem. So this memory coherence problem is different from the event loop. It's a different concurrent environment in multi-processing environment. It is a second topic for concurrent programming. So here has a CPU and there is a cache. We have edges and data. We would like to access the cache, and the cache talk to memory. So this is actually our caching hierarchy. So if the data is already in the cache, then we actually do nothing but get the data to read them in or write out. So let's write, but if actually you don't get the data from cache, then you need to access the memory. Then you have the no write, write through, and write back, 3 different schemes. So what is no write? No write, which write invalidate cache and then go directly to memory. That's called no write. So let's go back to here. So right here we have a processor. We have processor, and it demands for some variable called x. And this x copy actually has, here you have x, here you have x, and now you need to, and then the memory has the common copy of x. These 3 copies need to maintain the consistency. So if I want to actually access this x, I want to modify it. One way to do this, you actually write through here, and then actually now that's write through. And the other one is called write invalidate. You don't write through to here because this actually takes more cost. So what you want to do is actually for write invalidate. You actually write to this x, so this x got updated, but you invalidate all the copy that is existing in other cache. That's a write invalidate. So you have a write through and write back. Write through is write directly, write back is actually write to here, so only you have the copy. But if other processors try to access the X, you will then go to LAN and go to other processor. It's called write back. So there are different models: write through, write back, write invalidate. So write through will go to the main memory and cache. Directly write your own cache copy and the memory copy. Write back, CPU write only to cache, but actually later when people access, you will write to actually the memory later as a block. But actually there is also a write invalidate. You will actually write to your cache, but invalidate the cache copy and then other caches copy as well. So that's write operation. Read operation usually had no such problem. So right here we had a Snoopy cache coherence protocol. We have write update, write invalidate, and write back. So here let's compare the different schemes. So other processor issue have been discussed in other chapters. So right here let's look at this different mechanism. We have a write update Snoopy bus. And here the processor will write x equals 100, but actually is a copy in the memory that is actually 505, and there's other cache that is also has a copy 505. We are writing in such environment. So here we have the write back cache. First, CPU A read X, and then miss for X. And then CPU B read the cache, and then cache miss for X. Here we have different activities. So right through, it will go through here and then directly update here as well. Write back will hold here but invalidate other copy until you actually been read by some other people. You write to the memory and then to other cache. Here is the write update, and we process a reads from X, and then there's a cache miss for X. Then the content of the cache is 0, and then content of memory location is 0, and you will have a copy go back to the cache. If we have a cache miss, same thing, you got a 0 over there, and then CPU write a 1 to X, then you will write broadcast to X. So there is another way called write broadcast. Write broadcast is that if when you write X equals 100, then you have a bus transition to broadcast for other people. And the Snoopy bus is like when you actually write, it will check other cache content and then will update it while your bus has extra bandwidth. That's called Snoopy bus. Concurrent Programming Fundamental 1, Languages, Lecture 3. Language and libraries. This is quite an important topic of what are available in the concurrent parallel programming paradigms. We have language, we have shared memory model that we talk about it. That's mainly for a local environment, the shared memory model. And we have message passing for multi-programming, multi-processing. And we have distributed. So message passing and the shared memory can be on desktop, and message passing and distributed computing can be actually in the multi-program or remote site. So the shared memory model, we have the Java C# for a shared memory model. Both of them have a thread control. And the extension package, we have the Open MP multi-processing model. And then library, we have the pthread for Linux and Win32 thread. And message passing, there is a MPI message passing interface library. And the remote procedure code is used for distributed computing. There is the internet libraries. We will have some example for these. There is a very large number of experimental, pedagogical, and the niche proposal for each of these regions in the table. So we will see what are the current example for these. So the language for shared memory, we have these different languages. We have Java, C#, C++, R language. This is Rust language, Scala, Haskell. All of them has the shared memory model. And then we have message passing using the Go language. And we have the E language for distributed environment. And for the library, the package, we have OpenMP, multiprocessing. For the shared memory, we have a remote procedure call in operation system to support the distributed system to do remote procedure call. So this one actually is also called as RPC. And this message passing usually called message passing. And here you actually have a multi-threading multiprocessing. And you have a piece thread for Linux, Qt, the Windows.NET. And you have the SIM for this, and you have the MPI. Thread creation. To become parallel, first you need to create a thread. Almost every concurrent system allows thread to be created dynamically. So it's runtime. You actually don't actually at the compile time to deal with the creation of the thread. Syntactical and the semantical detail vary considerably from one language to another, and library as well, and most conforming to one of the 6 principles. So there are 6 principal options. Co-begin, parallel loop, launch at the elaboration. Elaboration is declaration. Fork, implicit receive, and early reply. So here are 6 different language mechanisms defined in the languages. Here I have the co-begin, parallel loop, launch at the declaration, fork and join, and then implicit receive, and the early reply. The first 2 options delimit thread with special control flow construct. So actually has the parallel for loop. That's actually a special control flow construct. So these 2 actually is at loop level, you do a parallelism. And launch at the declaration or fork and join, you actually provide some function for it to run. And here may have the implicit mechanism or early reply mechanism behind the programming language as well. So thread creation syntax, co-begin. In C#+, we have co-begin. So actually we have the language programming, and then you put different statement in there, and these different statement will be run in parallel. In C++, we can include an open multiprocessing package, OpenMP, and then you type the number pragma OMP, and then write section, and then you actually put different section with as a cobra. And all these different OMP sections will be run in parallel. So in C, C++, OMP iterative, all begin with the pragma OMP. The number sign or sharp sign must appear in column 1. So you have to actually know that it should be in column 1. Most iterative, like those shown here, must appear immediately before the loop. So you cannot actually put too many lines after it. And then you use the curly braces as the begin and end. This one is called begin mechanism. Second, parallel loop. Some language like C# have a parallel FX library that we mentioned in previous slides. This C# concurrent environment has the parallel FX library. So actually, this is like for C, C++, you had a OPM interface. So you actually write this parallel for loop format, and then you had a C# with the parallel.for, and you put your number of thread and variable I into there, and then iterate from 0 to 3. And fortunately, you have the for all to allow this to be done in parallel. A parallel loop C with reduction in open MP. Optional clauses on parallel derivative can specify how many threads to create and which iterations of the loop to perform in which thread. They can also specify which program variable should be shared by all threads. So there might be some reduction. So default shared, every variable will be shared. And then you can have the reduction plus some. So actually, what's that? You can actually, in this, the schedule static clause indicate that the compiler should divide the iteration evenly among the threads. So this one actually say for all the parallel loop, it should be even. Default shared clause indicate that all variable should be shared by all threads. So all variables should be shared. Reduction clause make an exception. Every thread should have its own copy, and the copy should be combined with the plus at the end. So this actually, the array itself is shared because they are read-only. So the default will all be shared. You got the same copy from different parallel tasks, and then the sum actually is reduced. So it actually, you will have different copy you can modify to it, but at the end, they will be summed together for the sum. Launch at the elaboration. Elaborated task in Ada. In several languages, Ada among them, the code for a thread may be declared with syntax resembling that of a subroutine with no parameters. So you actually can have a procedure that's actually a program, and then you can define several tasks inside there. And this task will be forked out when you actually call P, and the P has the main thread, and T task will run as a by task, and two will eventually join. So task T begin execution as soon as the control enter the procedure P. And if P is recursive, there may be many instances of T, so T can be forked out several times as well. The main program believes like an initial default task. When control reaches the end of the P, it will wait for all appropriate instance of T to arrive and then complete the function. So actually that launch at declaration is actually a static assignment. You actually, at compile time, you know that these two parts of the program will start together. Now let's look at fork and join. Fork and join has no language structure. There's no pre-assigned parallel processing, and fork and join are used using the program function to achieve it. So here we have an easy writer, and it actually extends thread, and then there's a long function, so it actually is a callable function. Excuse me. So it actually is a runnable object and or runnable function. So you actually create a some new image render, and then actually you can use render that start the program, and that actually will run the run function. And then at the end, you can have the render.join to join the different tasks together. That's the fork and actually the join. So the lifetime of the thread, actually, you can, at the fork time, you will fork out different process. And this actually A part is using the call begin and parallel loop or launch at the elaboration. So it actually branch out at the same time for multi-process or double process and will join at the same time. But the fork and join actually will depend on when you start the fork or start and then when you decided to join. So the lifetime of the thread is different, and fork and join are more flexible. If you can see, you can mimic all the function by call begin or parallel loop. Thread creation syntax, implicit receipt. Implicit receipt, we have assumed that all our examples so far that newly created thread all run in the address space of the creator. So actually, it is on the same machine or memory structure. The RPC system, remote procedure call system, is often desirable to create a new thread automatically in response to the incoming request for some other address space. For example, I have a server I keep running, but if there's a HTML request to my server, then I will fork out a process to serve the client, but my main server will continue because I'm going to have other service requests from the client. So that actually is a implicit receipt mechanism to create a thread. So rather than have an existing thread executing the receive operation, a server can find a communication channel to a local thread body or subroutine. With request come in, and new thread springs into existence to handle it. In effect, the bind operation grants remote client to the ability to perform a fork. So basically, here your remote request will be granted to fork out different processes on the server, and if it is done, the data will be returned to the client side. So early reply, there's another mechanism called early reply. Modeling the subroutine with fork and join, we normally think of sequential subroutine in terms of a single thread which saves its current context and then execute the subroutine and return what it is doing before. The effect is the same. However, we have two threads. If we have two threads, one execute the caller, another execute the callee. And this actually fork and join pair is different from the caller-callee model in the procedure call, and they may have different results. Caller wait for the callee to terminate before continuing the execution. Nothing indicates, however, that the callee has to terminate in order to release the data to the caller. All it really had to do is complete the portion of its work on which result parameter depends. So here, concurrent programming fundamental number 2, implementation. So number one part actually, we talk about the multi-threading concept, and now we actually number one, we talk about the language models, and we have 6 different language models for it. That's in the language mechanism. And then that's actually operable concept. And now we'll talk about what is used to implement these different language models. So here, the first one is the multi-threading. So on the right hand side, we have a multi-threading. That's its task level parallelism, you actually when you have a fork join or something, you start different task, and then there is an aggregation task point. And if you explore the parallelism in data level, it can go down to operational level or instruction level, that you actually will actually branch out the data and then do fully parallel processing. We call it vector processing. And in fact, vector processing is more powerful than the this kind of task level parallelism. So here we have the two-level implementation for thread. We actually have thread, and then we have a process, and process will be scheduled to processor core. That's called two-level threads. So thread belong to some of the program, like some process one program, and then there are several threads in one process. And then this thread will actually sometimes have another process, and process will own this different thread. So there's a scheduler from thread to process, and then a scheduler from process to CPU as well. So that's called two-level implementation for thread. And then for Java, we have the main program, we have package collection, we have event dispatcher, we have timer, we have user-defined functions. They all can be the thread on the thread scheduler. Java memory model. In Java memory model, we can see that the runtime data area have multiple threads. And in each thread, you keep track of the PC program counter and different data for cache coherence. Per thread, we have thread 1 to thread n, and each one we have actually its own per program counter register and stack, and maybe multiple frame, and we have a native method stack. So that's thread information. You have program counter, local stack, frame, local variable array, operand stacks, dynamic linking mechanism, native method stack. And concurrent programming fundamentals. Scheduler gives us the ability to put a thread or process to sleep and run something else on its process. So basically, each thread will have new state, ready state, run state, and wait state. So running state is running, ready state is available list. And if you finish or got kicked out from the running state, you will be put into the waiting state. Until you are actually finished, then you will get from ready state to the terminate state, or you actually come from the running state to terminate state. So these are the states for these threads. And current thread is for running one. Ready thread is the waiting one that is in ready state. And current one is the running state. And then we have wait for the condition full. And we have also for the waiting list. Uniprocessor scheduling. At any time, a thread is either runnable or blocked. A runnable thread is running in the ready queue. A queue is prioritized. It's using round-robin method or preemptive round-robin format. To yield the processor to the other thread, run with schedule. So when you run the schedule, you give up your control on the CPU. If time expired or blocked, a thread can yield the processor to one other thread and return to the queue. To enter into wait state, run sleep on. So you have run reschedule, you have run sleep on, you have yield function. And cooperative multitasking. Long running thread must yield at a certain point to be fair. So that's preemptive. You actually have to be nice. Don't occupy CPU all the time. So that's preemption. Under time, we actually have a timer, interrupt, or signal to trigger involuntary yield. That's called preemption. Requires that we protect the scheduler data structure. So basically, before we make a program to yield, you actually need to disable the signal, don't allow the signal to interrupt the processes, and then enqueue the ready list to current and do reschedule. And then after you reschedule, pick the right process, and then you enable the signal, allow the interrupt again. So that's the procedure for preemptive call for yield. Note that the reschedule task take us to a different thread, possibly in call, other than yield invariant. Every call to reschedule must be made with signal disabled. So signal disabled is very important to maintain consistency. And must re-enable them upon return. Once it returns, you need to re-enable it. So here is the multiprocessing scheduling. So that's a multiprocessing scheduling. And we can extend our preemptive thread package to run on top of more than one OS provided process by arranging, by sharing the ready list and related data structure. More than one thread will be able to run at once. That's the multiprocessing. In a single thread processor, actually is a share or mimic computer. The program will be able to make forward progress even when all but one of the processes are blocked in the operation system. Any thread that is vulnerable is placed in the ready list. That actually the ready list is the waiting list. It's actually the queue. The ready list is the queue waiting for the CPU to run. So when the process call reschedule, that's a change of the control. The queue-based ready list will give the longest waiting thread. The ready list of a scheduler might give priority to interactive or time critical thread, or to threads that last run on current processor. May therefore still have data in the cache. True or cross-site parallelism introduce races between cores in the operation in separate OS processes. To resolve the races, we must implement additional mechanism, synchronization to make scheduler operation in separate process and make scheduler operation in separate process atomic, so it actually can be accessed one by one, and actually cannot have the mutual exclusion access rate. You have to access with the mutual access request. So here we talk about the multiprocess scheduling, and likely with the relationship with the multitasking or multithreading. So we will look at the synchronization scheme in the next lecture, but we will stop here and wait for the next talk. Thank you. Bye now.